Well, the next thing we need to know how to do is find the sum of an arithmetic sequence. And I really should qualify this by saying this needs to be a finite arithmetic sequence. We can't really add up the terms of an infinite arithmetic sequence because the sum of all of those terms would just tend toward either positive or negative infinity. So we can't really deal with this. And I suppose even more so, the proper language would be arithmetic series. So the sum of the terms of an arithmetic series is given by this formula. And it's something that I would normally have you guys explore, but I'm not going to use video time for that. So for now, I'm just going to give it to you. So we have this formula. It's half of the number of terms times the first term plus the last term. And we'll show this in class, but for now, just kind of take it at its word. Where, again, n is the number of terms. So then Sn is the way of saying the sum of n terms, of the first n terms. This, of course, is our first term. And this is our nth term. Fairly straightforward. Plug in, solve, right? It kind of works. So the first term of an arithmetic series is -7, and the fourth term is 23. The sum of the series is 689. Find the number of terms. Let's work with this a little bit. Eventually, we know that we need to get to using this formula. But in no way, shape, or form are there only 4 terms in the series because, well, to get from -7 to 23, you're not going to add up those 4 digits and get 4 numbers and get 689. So we don't know u sub n and we don't know n. We know the sum, we know u sub 1. But we can work with this, and here's how. We know that the sum of the series is 689, so 689 equals n over 2. And we know that the first term is -7. And, well, for now, let's just call it this using our general formula here. Again, we know that u sub 1 is -7, so maybe I could actually add these together and get 14 plus n minus 1 times the common difference. And I've got too many unknowns still, right? I've got to figure out what this n is, which is really what I'm trying to solve for, so I'm just going to leave that alone, which means I need to figure out what the common difference is. So I believe we looked at a problem like this already. Kind of. Well, we looked at something that's going to follow the same process. We're just solving for a different variable. So we know that the fourth term is 23. But remember that we can also define this algebraically using that general formula. And I know that u sub 1 is -7. So 30 equals 3d, with a common difference then of 10. And now I've got some information that's going to help me get somewhere with this. So let's simplify it. Now we've got everything that we need. So let's cooperate here. Let's work with this. 10n minus 10. So I get -24 plus 10n. Let's multiply everything. Sometimes I like to multiply everything by 2 and just get rid of that fraction, but here I think it's going to make things a little bit worse. So, and I'm just going to reverse the terms here just to make things a little bit nicer as well. We're going to subtract, and wow, this is hefty. This is a tall order to factor. It is factorable, or you can plug it into the quadratic formula, and I might go that way. But since I'm looking right at the solution, then I'm going to just give you the answer. So this is going to factor down into 5n plus 53 times n minus 13. Well, then I'm going to get n equals negative 53 over 5, or n equals 13. So the question becomes, which one do I pick? Well, I want the number of terms in the series. I can't have 53 over 5 terms in the series because I need to count the number of terms in the series. So we can eliminate that one. N must be 13 because n must be a natural number, which is really just another way of saying the positive integers. So n is 13. There are 13 terms in the series. And that's that. Let's extend this out to a word problem. We want to see some application, so let's do that. Suppose you earned $38,000 when you started your job in 2010. You receive a raise of $225 every year. How much did you earn in 2018? In which year would you earn 50% more than your starting salary for the first time? Let's take this in pieces. How much did you earn in 2018? Well, this is a series. This is an arithmetic series. I have $38,000, and I'm adding $225 for every year that I've worked there, every additional year that I've worked there. So we can make a series out of this, a sequence out of this. So 38,000, minus 225. So 37,775 plus 225n. So that way when n is 1, my salary is 38,000 like it's supposed to. When n is 2, I get the $225 raise, and so on. Now, you might have noticed this isn't U sub 2010. This is U sub 1. So we're making an equivalency between saying that when n is 1, that refers to the year 2010. When n is 2, that's then going to refer to the year 2011, and so on. So we want to really be careful with this, and we don't want to call it U sub 2010. We want to call it U sub 1 because that's my first term in the sequence. So we have to be careful with our notation. But now that I've got a general term, I can do whatever I want with it. That should be 225. Oh, yeah, it is. Okay. So 2018 is going to be U sub 9. Right, 2010 is 1, so 11, 12, 13, 14, 15, 16, 17, 18. Yeah, U sub 9. So it's just a principle. It's just a matter of plug in and solve. So $39,800. It's a pretty nice steady increase. And there's my salary in 2018. The second question is going to involve a little more thinking. In which year would you earn 50% more than your starting salary for the first time? So what's 50% more than your starting salary? Well, 50% of this is 19,000. So 50% more than 38,000 is going to be 57,000. So I want to know which term gives me at least this much. So I want to know when is U sub n either equal to or greater than, but for simplicity's sake, we'll call it equal to and hope that it works out to an even number, equal to 57,000. Well, we can apply our general formula. And once again, it's just a matter of plug in and solve. So 57,000, I'm going to subtract 37,775. 19,225 equals 225n. So we're going to divide. And I get n equals 85.4, which means we're not going to round this down to 85. We want to think about this. if I round down to 85, then I haven't actually made it over the 50% mark. I'm close, but I'm not there. So we really want to call this in the 86th year, which means I should find a new job. Because if, actually this is not, yeah, this is your 86th year of working there, which would be the year 2097, if I'm doing that correctly. All right, n equals 86. Yeah, I think that is right. 2096 or 2097. Either way, that's a long ways away. And maybe I should find a new place to work. But you could see from the problem, it looks complicated, right? It looks impossible. In which year would you earn 50% more than your starting salary? Well, I don't know how to do that. I don't know how to figure that out. But we do, right? We can talk through the problem and we can solve the problem by logic. Say, okay, well, what is 50% more than 38,000? It's 19,000. Well, it's 57,000. So in what year is my sequence going to hit, in what term is my sequence going to be equal to 57,000? Or at least 57,000, and it's during the 86th term that you finally break that threshold, right? If I check this, my 86th year, my U sub 86 is 57,125. So I finally break that threshold in term 86. So we actually, even though it looks completely unfamiliar, we can compartmentalize and break down this problem in order to find the steps that we can solve and the steps that we actually know how to figure out. And all in all, it's really just a principle and a matter of just try something. It's not going to hurt to try it, because it's either going to get you to the right solution or it's going to eliminate something that wouldn't have worked anyway, which is also just going to get you eventually to the right solution.